Good morning, good afternoon, or good evening, everybody. My name is Matteo Aroni. I am based in Milan, Italy, and I work at ANSYS in the area of Fluids Application Engineering. In this presentation, I will try to introduce you to Ansys SimAI. We will talk about how this technology could fit your industrial processes. Finally, I will guide you through a list of CFD scenarios and use cases. Before going there, let's take a step back and make sure we can agree on a few concepts that we can then take for granted later. What do we want to refer to with the term artificial intelligence? In its broader sense, we call artificial intelligence the intelligence shown by machines, in particular computer systems, as opposed to the intelligence of human beings. So, if with the term AI we refer to any technique that enables computer to mimic human behavior, in the sense of complying with a predefined logic and set of rules, we talk about machine learning to indicate that the program is autonomously modifying itself to improve the way it accomplishes a given task. Deep learning is a type of machine learning that runs inputs through biologically inspired artificial neural networks. Generative artificial intelligence is deep learning supported artificial intelligence capable of generating text, images, videos, or other data using generative models. Generative AI models learn the patterns and structure of their input training data and then generate new data that has similar characteristics. SimAI is a generative AI cloud-based platform that takes any set of simulation results as inputs to train the AI model. Once the AI model is ready, and it can take up to 2 days for very large model and datasets, it can generate new simulation results on any unseen new geometry to feed the platform within seconds. How could such a powerful tool fit your company processes? We can imagine that any simulation and test results, whether coming from laboratory or from in-operation testing, could be uploaded to the platform to train an AI model. Anything in the range from dozens to thousands of data samples would be good for SimAI model training. Once the training is done, the resulting AI model can be labeled as an item in a catalog of AI models with any logic you may value. Now, when it comes to evaluating performance on new designs, the appropriate AI model can be selected from the catalog and consumed by simulation and testing illiterates beyond the traditional users. There are multiple ways to expose SimAI technology inside your company processes. One way is through the cloud-based user interface. Select the AI model you want to use. Upload your new design in the shape of a very loosely defined surface representation or triangulation. No need for it to be closed or to be representing a volume. Run the prediction. It comes with a confidence score, which is either a measure of the quality of the prediction or a measure of the training data representativeness of the new geometry. Once you have your prediction, you can grab the files and post-process them directly in the platform. By the way, let's take a step back. How did we create the AI model in the first place? As said before, a project here is a specific AI model. To the project, by drag and drop of individual data or entire folders, we add all the desired training content, we configure the inputs and the outputs in terms of variables of interest, and finally, we select the 3D space we want the prediction to address. Also, the training duration is intuitively controlled by a slider. One of the unique capabilities of SimAI approach is that both the training and the prediction are based on continuous functions dealing with the volumetric data. This enables a better understanding of the data and a significant flexibility to any downstream post-processing. The surface data visualization is just one of the possible options, and the method also ensures that different surface representations of the new geometry are leading to consistent and unbiased by mesh distribution results. Any global quantity measuring performance is obtained by integration of the relevant source data with increased robustness and consistency in any optimization study. Even on a model that we could consider very small by automotive aerodynamic standard, when we consider both the meshing and the solving time, SimAI prediction is close to 50 times faster than CFD calculation. When approaching generative AI in the context of product development lifecycle, we should probably take a closer look at the plot on the right that the platform is providing as part of the automated report that comes with any usage of the AI model. Here, the simulated and the predicted results are presented together with the training and validation data. We want our AI model to be precise in the sense that there is enough variability in the training data so that the prediction is not perfectly accurate, which could be resulting from overfitting, but is instead lying within a small acceptable tolerance, because this precision measures the confidence that next unseen geometry prediction will also be lying within the same tolerance from the simulation. Now, how can we capitalize on AI acceleration for this specific application? We can certainly imagine complementing previously isolated CFD simulations on selected car configurations or attitudes with a full and continuous sweep of data across the full range of possible car attitudes, very much alike what we are used to do within the wind tunnel once a car model or a prototype is built, overcoming, of course, the lead time required to get from the design to the prototype or actual product manufacturing completion, but also being competitive with experiments in generating a full aero map. Again, even if these slides gives a sense of how accurate the prediction can get with a training dataset that is homogeneous enough and with an unseen geometry well inside the design space described by the training data, the precision, or in other words, the maximum distance between the data and the prediction for the whole training and testing data population is the most valuable metric to chase, because this helps ensuring the confidence on any prediction on a new unseen geometry that is also similarly lying within the design space. Another way to capitalize on both AI acceleration as well on SimAI specific flexibility is exposing it very early in the design cycle. Here we see in the foreground a blended session from which, by means of PySimAI, the SimAI Python API, we have created a small script that sends the morpher geometry to SimAI and retrieve the predicted field back to make it available to the designer in any form, qualitative or quantitative, that would make sense to guide through the design space exploration. If you're interested in knowing more about how new technologies are impacting automotive external aero development, do not miss Pushing the Boundaries of Aerodynamic Design session at ANSYS Simulation World. It goes without saying that the more complex the physics and the longer the simulation duration, the higher the acceleration SimAI can deliver. In this heat exchanger use case, as you can read in the slide, we have 2 orders of magnitude speed up in the evaluation of the heat exchanger design efficiency. 250 conjugated transfer simulation results were used to create an AI model of the shell and tube heat exchanger, with topology changes in terms of the number of tubes, baffles, their orientation, relative positioning, and inland coolant velocity. With a SimAI outlet temperature error compared to the conjugate transfer simulation of less than 0.2% for the unseen design, we can reduce the current workflow by 99% and evaluate more than 3,000 designs at the time it takes to run a standard simulation. The additional complexity of this multi-phase free surface flow around a ship hull is making the CFD simulation longer, and then the speed up factor enabled by SimAI bigger. The size of the training data is less than 300 simulation results that cover the design space of hull shape variations combined with varying operating conditions such as draft and boat speed. With a predicted resistance error compared to CFD of less than 4% and a perfect wave pattern prediction, we can assess the performance of new hull designs in few minutes instead of days. Here we see another step up in complexity with a solid phase distribution that is immersed in a liquid filled stirred tank. This solid could be a product, a reactant, or a catalyst, in any case a key component of the device's performance. The free surface location is also called cloud height and is a critical measure of the process performance. This is a type of CFD simulation that runs overnight on a small cluster. With about 30 of these simulations, we can create an AI model of the steerer tank, including a significant topology change, such as the number of impellers. The AI model prediction runs thousands of times faster than the CFD simulation, and it can provide insight on the solid loading and assess the location of the liquid interface, or cloud height, within a few percent from the CFD result. A repository of all data could be used to build AI models that could predict the cloud height at the change of impeller type and number. Taking a step back in physical complexity, but emphasizing more the topology change, this is a battery thermal management problem, very instrumental in battery life prediction that is a critical success factor in the battery design. With about 10 accurate CFD results, we could create the AI model of the battery module, including its cold plate for cooling. The training data included different configuration of cell packs, liquid coolant need capacity, cooling inflow speed, and cooling channel diameters. The AI prediction on 8 new cooling designs takes less than 1 minute, with a maximum error of 2 Kelvin in the battery model and average error of 0.2 Kelvin. This accelerated topology exploration can be used to assess, in the earlier stage of product development, very different configurations, and at the later stages, to fine-tune the selection of the optimal shape of the cold plate design. Okay, here is another thermal reliability problem of electric components in critical environments. We used about 30 accurate CFD results to create the AI model of a forced convection cooling channel that is installed on top of a power inverter. The topology changes are larger in the design of the pins, and with an AI model temperature error compared to CFD of less than 2%, and an accurate flow field and pressure drop prediction, one can reduce electronic cooling system development time from 2 months typically to less than a week. It is clear that such an acceleration opens up the possibility to virtually test many more operating conditions even farther away from nominal design, and ultimately resulting in an increased product reliability. Now, to conclusion, are we moving the first steps in the new era of AI accelerated simulation? Will the product development cycle be revolutionized by AI? Okay, the talk today was not so ambitious as to try to answer these questions. We were just trying to humbly describe ANSYS SimAI, the cloud-based physics agnostic AI platform from ANSYS, touching briefly some fundamentals and possible ways of using it in a couple of CFD relevant use cases. I hope you enjoyed the content and wish you a productive stay at ANSYS Simulation World. If you want to know more about ANSYS SimAI and the other AI-related initiatives at ANSYS, such as ANSYS GPT, your virtual assistant for simulation, and ANSYS AI Plus, the set of AI-based solution augmentation, please visit ansys.com/AI.
You could say this is where it all began, with one of the most legendary brands in all of motorsport.
When they fire up the engine, I felt something difficult to describe. You know, sometimes a dream come true, but the story like my one can happen just with the Ferrari family.
The reliability of the CFD simulation for the Ferrari Challenge is the result of the finely optimized technology.
The Ferrari Challenge, the most renowned single-mark championship series designed for those whose passion for racing runs as deep as iconic red hues. I'm here in Maranello, Italy, at Enzo Ferrari's famous factory, to see firsthand how simulation continues to drive innovation at this house of performance and elegance.
If you consider that in the past, the total time that you spend to be ready was almost 2.5 years. Now, thanks to the simulation, in 1 year, we are ready.
For more than a century, mobility has been the beating heart of human progress, connecting us across vast distances, expanding our reach, and shaping our daily lives. But today, we stand at a crossroads like never before. With advancements in electrification and sustainable practices, the industry is undergoing a profound transformation, unlocking the future of mobility and driving us towards a world of limitless possibilities.
When talking about future mobility, it's really important to be more sustainable, to be more efficient, to reduce energy consumption of vehicles.
We literally have 6 million variants. And how do you validate it? You can't go about testing the 6 million variants on the roads or on our tracks. It's very difficult.
We are able to bring this component together to a very complex system, and it is a fully integrated, efficient, summed up solution.
The key enabler for us to do modularity is to have good simulation tools.
From the track to Main Street to the motorway, we've seen how simulation is preparing us for the road ahead and helping us reach the future of mobility faster than we could have ever imagined. But what about the places where there are no roads? Well, prepare to get a little mud on your boots, because today we're miles from the comforts of the design lab to see how simulation is taking us off the beaten path.
No one's driving it.
There is no driver here.
And more than 90% of the accidents are caused by human error. This can be prevented if we really let the car drive itself. And this is where simulation comes in critically.
No one's driving it.
There is no driver here.
And more than 90% of the accidents are caused by human error. This can be prevented if we really let the car drive itself. And this is where simulation comes in critically.